Hey guys, welcome back to my differential equation series. This is my first episode and ultimately the first quote-unquote lecture that you'll be getting on this. And before we start the actual solving differential equations, I just want to start with some basic definitions that you need to know. So starting off here, first definition, what is a differential equation? Well, a differential equation is an equation that relates a function to its derivatives. For example, we have dy dx equals 3x squared. 3x squared being the slope of y. So, the slope of y behaves like 3x squared. And if we were to solve this, we get y equals x cubed plus c. Solving it, we just do an integral. Basic stuff. If you completed Calculus 1 or Calculus 2, this should be very trivial to you. So, that's the differential equation. It relates the equation to a function. So what you'll see, especially with beginner differential equations, instead of having y equals some function of x, we'll have the derivative of y equals some function of x, or rather, the derivative of y equals some function of x and y. And that's what we're really going to get at here. It's a different form of equations, and that's what I like about differential equations. Yeah. So, our next definition will be order. You hear me a lot saying first order differential equations, second order differential equations. What does that mean? Well, an order of a differential equation is going to be your highest derivative appearing in the equation. For example, a second order differential equation can look like y double prime plus y prime plus y equals x, right? That's your second order because it's the highest power, or the highest prime rather, is double prime. The highest derivative is a double derivative of y. And that's the highest derivative that appears in the equation. So our next definition is a linear differential equation. You might think that a linear differential equation looks a lot like a linear equation, one in the form of y equals mx plus b. You couldn't be further from the truth. Nah, I'm just kidding. It's very different. And you shouldn't mix the two at all. I wouldn't recommend that because they are not like each other at all. A linear differential equation is a differential equation that has no powers of y. For example, no y squared, no y cubed, nothing. You can't have y times y. Can't do that. On top of that, your coefficient for any y prime or y double prime, any derivative of y, or even just y itself, cannot be another y. So example, you can't have y times y prime. You can't have y prime times y double prime. You can't have y times y double prime. And a good way to look at this is you can't have y squared. You can't have y times y. In the same sense, you can't have y times y prime. None of those work. You can't do it. And if you want to know why, I can explain in the comments. Just ask me. So yeah, our last rule that we're going to be looking at is the coefficients can only be independent variables. We're mainly going to say x, x squared, or c are independent variables. We learned this a lot in multivariable calculus or calculus 3, if you guys have done that. I didn't list it as mandatory in the prerequisites, so let's give you an example here. An example of a linear differential equation is y double prime plus 3y prime. Notice that 3, the coefficient, is a constant, so it's independent, plus xy. X is a coefficient that is independent from y. And that's going to equal sine of x, another independent variable. Now let's look at nonlinear. Nonlinear being y double prime squared. You can't have y double prime squared because that equals y double prime times y double prime. One of our rules is broken. Plus y times y prime. Again, another rule broken. Y times y prime is a product involving two dependent variables. I think you get the idea, hopefully. If not, again, ask me in the comments, I'll cover it for you. So why do we care if a function is linear or not linear? Well, let's look at real life examples. Take a linear example, and we're actually going to dive deeply into this in like a few episodes, so keep this in the back of your mind. We're going to look at a a spring mass system using Hooke's law. So Hooke's law states that the force of a spring is equal to negative k times the distance it's away from equilibrium. So if you stretch a string out or spring out, the force that's going to be pulling back towards this equilibrium point is going to be equal to a negative constant times the distance you pull back. Now this is actually a linear differential equation. We write F, the force, equals mass times acceleration, acceleration being the double derivative of x, and force equals negative kx. So now we have mass times x double prime equals negative kx. And we can actually put everything on the left-hand side and say m x double prime plus kx equals 0. That's a linear system, second order differential equation. It's pretty simple. We'll get to it soon. But what about a nonlinear system? What about air drag, for example? So air drag is, the force of air drag is proportional to its velocity squared, right? If we were to look at this in an equation, it would be mass times acceleration, m x double prime, would equal negative c, a negative constant is pushing it in the opposite direction of which it's falling, times the velocity, so the derivative of x prime, squared. In other words, the equation becomes mass times x double prime plus c x prime equals 0. Sorry, plus c x squared, x prime squared equals 0. Sorry, I was messing up. Let me repeat that one more time. M x double prime plus c x prime squared equals 0. That is not linear because that x prime squared is x prime times x prime, which is not linear and makes it way more complicated. This is now a non-linear ordinary differential equation. So one of the skills we're going to be building as we go through this series is trying to figure out what method we will use to solve the differential equation. I'm going to be showing you first how to solve a first order differential equation in one of the easiest and most simple methods in my opinion. So let me walk you through it real quick. We have a differential equation in the form dy dx equals a function of x and y. So for example, we're going to say dy dx equals x times y. We're going to separate this. We're going to say divide both sides by y, and multiply both sides by dx. Now our equation looks like dy over y equals x dx. In other words, we can simplify the left-hand side to 1 over y dy. And hopefully by now you can understand how to solve this, but let me walk you through the last step here. All we have to do is integrate it. We take the integral of 1 over y dy, and that equals the integral of x dx. And solving it, we get the natural log of the absolute value of y equals x squared over 2 plus c. And we're going to create a little rule here. You don't have to use this rule if you don't want to, but for my channel, what we're going to do is we're going to try to put c, the constant of integration, on the easier side of the equation. Here, x squared over 2 is easier than the natural log of absolute value of y. So we're going to put the constant of integration on the right side, where the x is. So if you've been taking math for a while, I believe it's pre-calculus where this solution is first brought up. But what we're going to be doing to solve this is we're going to put both equations to the power of e. So now what does that look like? We're going to say e to the power of natural log of the absolute value of y equals e to the power of x squared over 2 plus c. And the e to the power of natural log of absolute value of y, that's a tongue twister, that just equals y, right? That will just equal y. Y equals e to the power of x squared over 2, and we're going to separate that plus c. If we remember with exponents, say we have, I don't know, x squared times x. How do we simplify that? Well, that's just x squared times x to the power of 1. To simplify that, we just say x to the power of 2 plus 1, right? When you multiply exponents, you're just adding them. Now let's look at our equation here. We have e to the power of x squared over 2 plus c. If we multiply e to the power of x squared over 2 by e to the power of c, that equates to the same value of e to the power of x squared over 2 plus c. We're just reversing that law that we've learned back in pre-calculus, and that law will be used everywhere in differential equations. So what's our final answer? Well, e to the power of a constant is just a constant, right? E to the power of any constant is just another constant. So we're going to say e to the power of c is going to be c. So now we have y equals e to the power of x squared over 2 times c. In other words, y equals c times e to the power of x squared over 2, and that's our answer. And I'm going to show you a bunch of different functions that actually look like this that we might have used in the past before. Maybe we didn't know this was a differential equation, but here we are. I believe my favorite one is the function for continuous growth with investments, and that's probably the one I'm going to be showing on screen. It is PE to the power of RT. Notice what we did. P, the principal, the constant, E to the power of R, the rate, times T, time, right? Just lock that in your head. I believe you can notice the similarities, PE to the power of RT and CE to the power of x squared over 2. Notice the similarities, learn it, love it. Let's move on. So, this will be the last equation, or the last, rather, definition you're going to be learning of this lecture, and then you can go on with your day. We're going to learn the equilibrium solution. When a system reaches a state of equilibrium solution, it will stay there for any x. For example, a slope reaches 0 for any value of y, and x can't change it. For example, dy dx equals y times 1 minus y. So our equilibrium solution will be y equals 0 and y equals 1. Because when the slope dy dx equals 0, no value of x can change it. None. Right? Now, even if we did dy dx equals xy times 1 minus y. Let's look at this. Plug in the numbers. If y equals 0, we're going to say x times 0 times 1 minus y. Anything times 0 is 0. So no matter what x value is, the differential for y with respect to x will just be 0. No matter what. The slope of the line will just be 0. Now let's look at 1, right? With 1, we're going to say 1 minus 1 in the parentheses there is 0. Well, let's look at this. We have x times y, which is now 1, times 0. So we have x times 0, which is 0. So now we have dy dx equals 0 again. And no matter what value of x we set x as, the differential will never be anything but 0. Ever. That's our equilibrium solutions. We did something similar in Algebra 2 for a while now, actually, with factoring. And factoring will come into play a lot here in differential equations, as you'll see soon. But in factoring, we're taking usually a polynomial or a quadratic equation, and we're trying to find a solution in which x is 0. We're trying to find the 0 points. Here, we're trying to find a point where slope reaches 0 for any value of y that x cannot change. It's very, very similar. It's just like that. We're saying, when does y prime equal 0 for any value of x? That's it. That's all you gotta wrap around your head. It's a lot more simple than a lot of people make it out to be, usually. And we're gonna stop right there. Next video, we'll be covering slope fields, and let me look for my notebook real quick. We're gonna be covering more solving of linear first-order differential equations, and we're actually gonna learn the integrating factor method with mu of x, e to the power of integral px dx. We'll cover it all when we get there. It's going to be really fun. So please stick around. If you like this video, let me know. This video was a lot less scripted than usual, which you guys can probably tell. If you like less scripted videos and more, I guess, human videos, let me know. Or if you want me to change it and be more scripted next time with less gaps and pauses, please let me know. I love your guys' input. Thank you guys for sticking around. I'll see you next video, all right? See you guys.